Okay, I'll go ahead and do the introduction, then turn it over to you. Professor Christine Ehlig-Economides is a professor, and Hugh Roy and Lily Kranz-Cullen Distinguished University Chair at the University of Houston. Prior to her current position, Ehlig-Economides taught at the other university here in Texas A&M, of course, for 10 years and worked 20 years for Schlumberger. While at A&M, she managed research in production and reservoir engineering and conventional and shale reservoirs, and helped the Petroleum Engineering Department to grow and evolve to a broader energy scope. Ehlig-Economides was elected to the U.S. National Academy of Engineering in 2003, was a member of the National Academy of Science Committee on America's Energy Future, and the NRC Board of Energy and Environmental Systems. She chaired the Academies of Medicine, Engineering, and Science in Texas Shale Task Force in 2017. She is currently a board member of QRI. She became an honorary member of the Society of Petroleum Engineers in 2018. Ehlig-Economides earned a Bachelor's of Arts in Math Science from Rice University, a Master's of Science in Chemical Engineering from University of Kansas, and a PhD in Petroleum Engineering from Stanford University. Professor Ehlig-Economides, thank you very much for joining us. The floor is now yours.
All right. My apologies to everyone. Are you hearing me okay? Somebody just wave.
We can hear you.
Okay, great. Thank you so much. All right. So we're a little bit of a late start, so I'll maybe try to watch my time to cut some of the remarks a little bit shorter. So I call this the ET apps. Last summer, I worked on 3 different papers related to energy transition subjects. And I think these are all near-term possible. So I hope you'll find them inspiring. So let's see if we can make the slide move. All right, here we go. So these are the 3 we're going to look at. First, carbon neutral crude oil, then blue hydrogen, and finally an enhanced geothermal system. So it's always useful to start with the hydrocarbon resource triangle, and it's a nice nod to Steve Holditch. So if you've ever seen a talk by Steve Holditch, you probably saw the resource triangle. And near the top where it's small, you have the conventional reservoirs that are kind of the subject of the past. Certainly in North America, we've gone well past this into the unconventional reservoirs. So they represent a lot larger volumes, but they're harder to develop. And on the right, we see this arrow that reminds us that improved technology usually also goes along with increased price. And so it was a bit of an enabler to see very high oil prices showing up around 2008, and they really enabled us to take over with these unconventional approaches. And at the bottom, we've still got the future with gas hydrates and oil shale, the Karajan oil shale, and these can be volumes, especially the natural gas hydrates, that eclipse all the other gas, and there's already a lot of that. So let's start now with the carbon neutral crude oil. So what do I mean by this? So I mean that we're going to talk about all 3 scopes. So scope 1 is your oil production and upgrading. That is directly related to upstream operations that petroleum engineers dominate. Then we get into the midstream and the refining, which are scope 2 emissions, but still very much under the control of your vertically integrated oil companies. But to the right are the scope 3 emissions that are mainly about the combustion of crude oil products. And so if we're talking about life cycle greenhouse gas emissions, more than 80% of those emissions are from the combustion of our products. So when the larger multinational companies talk about net zero, you need to listen carefully. Do they mean net zero for scope 1 and 2, or just scope 1? Or do they mean really we're going to worry about the combustion of our products? Because if we sign on to the concept that greenhouse emissions are related and causing climate change, then most of them are over here. And so just cleaning up our act in the upstream isn't even remotely enough. So carbon neutral fuel is going to cover all of these. So let's look at this coming from IEA. Gives us a little more of an elaboration on the nature of these different parts of the emissions in the life cycle. And this graph is showing kilograms of CO2 equivalent per barrel of oil equivalent. And so what we have are reservoirs ordered from smallest of this emissions to largest. And so each band like this is a reservoir. So a long band is a big reservoir because this is how many barrels, million barrels per day the reservoir produces. And so you can see the color coding. So the scope 1 energy for extraction is the pale blue. We've got flaring in the dark blue. Methane emissions in this green color, refining the yellow. So you can see the green and the yellow are a huge factor in the total emissions. And then transport is, for the most part, not so much. And people look at this and they wonder, wow, we don't emit that much methane. True, we don't. But this is kilograms of CO2 equivalent. And you may know that methane is counted as roughly about 30 times the greenhouse or global warming potential of CO2. So the actual methane content compared to the rest of this, which is mostly about CO2, is 1/30 of the height of the green that you're seeing here. This graphic says nothing about those scope 3 emissions. So we're talking about less than 80% of the total problem. So here's another graphic you've probably seen. This came out in late 2019. And it's a very sobering graph because we're looking at the National Petroleum Council report graph showing US, CCUS, or carbon capture utilization and storage costs in dollars per ton of CO2 emitted or otherwise emitted. And so these are looking at the largest 80% of the stationary point source emissions. Total emissions are actually much more than what this covers. And it's important to understand a little bit about the nature of these costs. So we've got 3 examples right here, and we can see a little bit of a breakdown in the total cost. So you could read off the graph. This is a total of 46, but $29 of that is in the capture and 17 in the transport and storage. And so if you look at cement or natural gas power generation, what you see is the transport and storage remains pretty small. And my understanding is $20 a ton is a pretty good round number, rule of thumb. And the real expense is in capturing CO2 from point sources. So this part, this dark red part, is what petroleum engineers can exert our skill sets toward. But we need to rely on our friends in chemical engineering for this capture part, and it remains very expensive. And this graphic also excludes the scope 3 emissions. They're over here in the part that isn't shown. But this is pretty scary. It ramps up pretty quickly to nearly $300 per ton. But here's another sobering reality, and that has to do with pore space. So let's compare the fossil energy sources. So starting from coal, you know, you can actually mine a cubic meter of coal, and it's all coal. So if you want to store the carbon dioxide from combusting that coal, first of all, the density change means it takes 8 times the volume. But if we're going to store it in pore space at 20% porosity, the bulk volume now is 5 times that. And then if we would like to get to at least the first level of fixing of the CO2 so that it's at least dissolved in the brine that we might store. So we'll go to a saline aquifer. It's 2% the saturation of CO2 in brine. And so multiply again by 50. So, you know, it takes on the order of 200 cubic meters to store the CO2 if it's really dissolved. That starts from a cubic meter of coal. Now, things are better for oil because oil starts from porosity and CO2 density is only a little less than oil. So maybe it's around 2.3 times the pore space. So the bulk volume that you would need to cover the emissions from combusting coal. But very interestingly, natural gas, it goes the other way. The CO2 from combusting methane actually occupies about 2/3 as much space in a reservoir as the methane did from where it started. And then on the right, just another little fact to keep in mind. People have talked for years about trying to clean up coal by storing the CO2, and they act like all you have to do is just, you know, compress it into an aquifer. But water is about as compressible as wallboard, you know, and so you're trying to put CO2 in pore space it's already filled with an effectively incompressible liquid. So you're going to have to pressurize that pore space, and you're not going to be allowed to pressurize it too much because you don't want to risk breaching your seal or fracturing through it. But if instead you think about injecting the CO2 and displacing brine, so produce the brine. So this is kind of like primary oil production and secondary or water flooding oil production. So primary injection and secondary injection, where you displace brine as you inject the CO2. And you can see you can get far more potentially into the aquifer if you do that. Of course, it's not free, but it certainly gives you a lot more efficient storage. Now, this work is done at the BEG, so I guess you may know some of the people involved with this work. It's a very, very interesting study, but it's challenging to understand what these authors have done. I think Professor Lake was involved in this also. And so they're looking at the life cycle analysis for what some have called EOR+, so enhanced oil recovery, of course, and then the plus means, but using industrial sourced CO2. So, you know, we have decades of very good experience with enhanced oil recovery using CO2, most of it actually in the Permian Basin in Texas. But most of that CO2 has come from reservoirs. It has not been point source CO2. And so this study is looking at, in a very interesting way, whether this sort of an operation is actually green net zero. And so the carbon neutrality, again, net zero all the way through combustion is what I'm talking about. And so they talk about different system boundaries. it depends on what boundary you put, what conclusion you come to. But they also mention it kind of matters where that CO2 comes from. And if it's already been credited to cleaning up coal, then you can't credit again to cleaning up your oil combustion. So my conclusion is that EOR plus using CO2 to produce oil, it's great for producing oil, but it is very difficult to get carbon neutral crude oil as I would describe it. You might get a little closer if you take CO2 that comes from ethanol plants, but that's not 100% okay either, because to produce the ethanol, you're emitting a lot of CO2 from combustion of the diesel for the farm operations. So this one is hard to get there as well, but it's easier probably than trying to use CO2 from a coal-fired power plant. And these sorts of ideas are facilitated certainly by the 45Q tax incentives. And you could also try to sell the produced oil to California and maybe make use of their low carbon fuel standard. So people have talked about a pipeline to the Permian Basin area. I think they're connecting up to the pipelines from these reservoirs for CO2. And so you can see connecting up ethanol refineries to collect CO2 for EOR plus. But I want to give you a different idea. So we're going to start from tight oil, so low perm oil. And if you're watching Texas and North Dakota show a lot of flaring. And I really think this is a black mark for our whole business. I'm very sorry to see that we do the flaring. And what is flaring? Well, the thing is that these tight oils are very light. They're very gassy oils. So they have a lot of associated gas. And so this graphic is looking at, again, color-coded, how do you use associated gas that's produced with crude oil? So the good certainly is marketed. So they call it takeaway in the Permian Basin area. So if you can find a way to sell it, perfect. Also, maybe you can use it for on-site operations. So purple, that's fine. But if you can't use it, at least flare it, because of what we saw earlier, that methane is so much worse than CO2. You don't want to vent your associated gas. That's what this yellow is, because that's methane, and it's 30 times worse than the CO2 you would get by at least flaring the associated gas. So we are flaring in Texas, much less than they flare in North Dakota, but we are still flaring some. And when I first did this study, it was actually a bigger fraction. Since then, we have some pipelines that have connected associated gas in the Permian Basin to more natural gas power generation. So when you have associated gas that you can't market and you can't use, and you're flaring it anyway, it's stranded. How about if instead of flaring it, let's use it to run a direct air capture unit. So you may be watching Occidental, and they're talking about they're going to construct a DAC unit, but their idea inspired what I'm telling you. But what they are doing is not quite the same as what I'm describing. And I'm not entirely sure exactly how they are getting to carbon neutral crude oil. But they inspired me to think about, how do I think you could get there? And so the carbon energy unit that looks like this, it looks to me like it could cost as low as on the order of $58 per ton of CO2 if you're using gas that you can't sell. So I'm using a cost for gas that is stranded and otherwise flared of about 20 cents an MCF, which is the cost of gathering it. So if you were going to use it for artificial lift, that's what you would roughly pay. And so this can bring the cost down a lot. So this is a crazy idea to get CO2 out of the air. You know, it's what, 0.04% of a molar composition in the air. It's ridiculously low. So you need a lot of energy to separate it out. But if the energy you have is essentially free, maybe this makes sense. And so this is lower cost than a lot of the point source captures we saw in the NPC graph. It is more expensive than some of the offset negative emission technologies or nets, but it has a smaller land footprint and is very verifiable. And so what I found is you get to near break-even cost with the 45Q. This slide is before I've done some recent calculations. So what I would say is your best bet is CCS for using this gas rather than selling for CO2 because you get a bigger tax credit with the CCS or just storing in the saline aquifer. So this is interesting. If you look, where is it possible to do this? Well, all of the tight gas is very gassy. And what you need is roughly about 3,500 SCF per stock tank barrel. That's enough that you can offset the CO2 that will happen from combusting the CO2 or combusting the crude oil products. And so you look and you say, well, these look like they're too low. But the thing is, this is the solution GOR. The produced GORs are much higher. And so what I'm suggesting might work for any of these tight oils. Now, the big fields like Bergen, Gawar, Tengiz, unlikely they're going to be able to do this because really big conventional oil fields, you're going to go to water flood. And so you're not going to allow high produced GOR. But here's some reservoirs here that actually do have already high solution GOR, so they might be candidates. So look at that, tight oil has an advantage over big oil if we want to go to carbon neutral crude oil. So what's good about all this is somebody admit, I'll do it. We don't need to change anything about refining and products use. There would be new jobs for the carbon storage, and we avoid any worries about abandoning crude oil. But it doesn't stop the urban pollution associated with NOx, SOx, and volatile oil. For that, we need to look at my next suggestion. So please recall, this works when you have stranded associated gas from very light crude oil. So enough of that to collect enough CO2 to offset the crude oil products combustion. And don't think of this as a fantasy because this was the headline in June last summer. U.S. Occidental supplies first cargo of carbon neutral crude to India's Reliance. It was 2 million barrels. So again, I don't know exactly how they get to carbon neutral crude oil, but I think that for not very much more per barrel, we could offer consumers carbon neutral crude oil, where we've covered the externalities by carbon capture for the combustion of the subsequent combustion of the products. But I like blue hydrogen even better. So let's talk about that. So the idea of blue hydrogen, we're going to generate hydrogen from natural gas, capture the CO2 from the hydrogen generation, and then store it. And my suggestion is store it back in your natural gas reservoir, because I already showed you that you certainly have enough pore space for that. So the idea might be that in the future, some of our natural gas production will take blue hydrogen away from the field, and instead of the methane, instead of the natural gas. So about the colors, this is just, I don't know, we have this terminology. So if you're using electrolysis to produce hydrogen, that means you're going to use electricity to break water molecules. So it starts with water and makes hydrogen. If your electricity source is solar, it's called yellow hydrogen. It's green if it's solar or wind. For some reason, certainly nuclear power plants have plenty enough energy for electrolysis, and they get all three colors, red, pink, or purple. You can also gasify coal. So you can make black hydrogen or brown hydrogen. And if you do it where you collect the CO2, then, effectively it's like green hydrogen. It just used a fossil molecule to get there. So for natural gas, we go to the steam methane reforming, and we're already making a lot of hydrogen in the Gulf Coast area, mostly for the refining operations. And most of that is what's called gray hydrogen. So you are using steam methane reforming, but without collecting the CO2. But if you collect the CO2 and store it or sequester it, that becomes blue hydrogen. And another possibility is what's called partial oxidation, which actually produces solid carbon. But I don't find that a very attractive idea, but the blue hydrogen looks really interesting to me. So here's another diagram to clarify this a little bit. So here we've got actually natural gas and water. It does require some water. Some of your hydrogen comes from the steam. So it's steam methane reforming. And if you emit the CO2 from that operation, you get hydrogen, but it's called gray hydrogen. If instead, though, you use natural gas and water coming in, hydrogen going out, and capture all the CO2 and store it in the ground, that's blue. And then green hydrogen, of course, is you've got hopefully renewable electricity, and you use electrolysis with water as the feedstock. Out comes hydrogen and oxygen because you broke H2O, right? All right, so an interesting point is that it requires half as much water to do blue hydrogen as what's required for green hydrogen, because in this case, all your hydrogen has to come from the water. In this case, half of your hydrogen comes from the methane. However, I have recently become aware of a Stanford process that would enable using brine for the electrolysis for the water here. I don't know that you can use brine for steam methane reforming. So this looks like a real breakthrough for the green hydrogen approach. But as for now, blue hydrogen is way less expensive than electrolysis. So this comparison shows that. So here we have it roughly $2 per kilogram. Steam methane, this is gray, and then these are blue, and this is particularly blue. So this is with 89% capture of the CO2, slightly over $2 a kilogram. And there's a big range for the green for the solar or the wind. And, you know, people hope that sometime in the future, these will be more competitive. But for now, blue hydrogen is definitely, if you want to start migrating towards hydrogen, it would be a good move to start with the blue. Lots of gas. We are not running short of gas. So a little bit about hydrogen economy. But I need to watch our time. But this is an old graphic of coming from more or less this time frame when the Bush administration, this is the second Bush, went towards a $1.2 billion hydrogen fuel initiative. And why? Because of worry about dependence on foreign oil. So in this time frame, we were approaching 60% of our consumed crude oil products coming from imported oil, and it was becoming more and more of a strategic concern. So yes, also it is mentioning here about low pollution and no greenhouse gas, but the first concern was about energy independence. And stare at this all you want, you will never see anything about fossil anything on this side. So this is a hydrogen economy with no oil or gas or coal. And there was talk of the Freedom Car and using clean hydrogen fuel cell vehicles by 2020. 2020 is now, and the energy mix is still 88% non-renewable energy. So it didn't get there. But I would venture to say that the petroleum industry wasn't very supportive of a hydrogen economy that had no oil and gas interest in it. But that was then, and this is now. So this is a bit about power generation and the importance of natural gas to it. So I'm going to skip through this rather quickly, but this study shows that your lowest cost option for completely decarbonized electricity generation is natural gas supporting renewables. If you go to pure renewables, which is this sort of cases on the right, what you see is you need twice as much generation capacity. And I think that's probably underestimating. So all this talk of going to pure renewables, well, we have a long way to go, and you have to go twice as far as what you do over here to even get there. So something else about the blue hydrogen, if we think about using the natural gas reservoir to store the CO2. So let's suppose we produce the methane, use that to make SMR blue hydrogen, and then store the CO2 right back at the same reservoir. It turns out that CO2 can enhance your natural gas recovery. So you might want to kind of integrate this sort of idea. And so these are looking at potential places where gas reservoirs might be. And the thing is that you may need to store your produced blue hydrogen, and very often the reason for these distortions in the bedding, the traps, are salt diapers, and that is currently the best place to store hydrogen. So you create a cavern by circulating fresh water and dissolving salt out. So you can kind of put all this together. It could be quite a convenient idea. We'll not be running out of natural gas anytime soon. No time to belabor this point, but there's a lot of natural gas. The point of this slide is that blue hydrogen could be used for power generation at costs that are already essentially competitive with current practice, especially if you go towards the, well, actually, no, especially if you look at your lower capacity. So these are these peaking plants that come on just when we have a big power load. So hydrogen into the power generation looks like a very good idea. And the thing is that this comparison isn't even using the most efficient power plants, which would be fuel cell based rather than combusting the hydrogen. So if we look back at our NPC graphic and consider the level of 45Q support, my estimate is carbon neutral crude oil is just a little bit more expensive than what 45Q supports, and blue hydrogen is very attractive because the captures associated with blue hydrogen are low cost capture. And does anybody care about blue hydrogen? Well, in California, they have this beautiful car called a Mirai. And so they're driving it. I think they're paying at least twice what they should for the hydrogen fuel, but they do demonstrate that it's a car you might like to have. And why might you like to have it? Well, because, you know, everybody's pushing the BEVs, the battery electric vehicles. If you own one, as I do, you very quickly learn that most of the chargers, the level 2 chargers, take twice as long to charge as it takes to use the miles that you just charged. So there are superchargers, but they also take 20 to 30 minutes. So it's nothing like this lady over here. She's going to refuel her fuel cell electric vehicle in 5 minutes. So for me, as a petroleum engineer, this blue hydrogen idea looks very attractive for transportation. Most people don't think so yet. Lots of other ways to use hydrogen that are summarized here. This is from a Shell study, and this is all transportation uses, and some of which have very high technology readiness and others not yet so high. But boy, I mean, I'm attending CERAWeek right now, and you can hardly find a moment on that program that doesn't have something about hydrogen going on. So this is a big subject right now, hydrogen. What should keep you awake at night would be the methane emissions. So satellite images show these methane emissions. When you look at oil and gas satellite emissions, what you see is that it's the upstream where you're emitting methane, not so much the refining downstream on the coast. It's more the upstream. So if we're gonna, if blue hydrogen is an attractive idea, we got to stop the methane emissions, or it will not fly. Wetlands make a lot of methane too, but okay, never mind. All right, so the blue hydrogen, I think I have found more than one resource that would suggest it should be competitive with gasoline and diesel. In California, it's overpriced. It does require new infrastructure, but we have a lot of pipelines for methane that you might use that infrastructure towards hydrogen. Ultimately, you may want dedicated pipelines, but you may be able to mix hydrogen with methane to get the distribution started. Very quick refueling, no pollution. I mean, when you use a fuel cell EV, it gives off water vapor. So no NOx, no SOx, no volatile organics. And as the other slide from Shell showed, definitely looking at for air and sea, not just roads and rail. It's less expensive than business as usual for peaking power today. And it doesn't make, if you go to fuel cell power generation, you don't get nitrous oxides. If you combust the hydrogen, you will. All right, so summarizing on that, blue hydrogen is a carbon neutral transportation fuel. Well, it is and it isn't. The hydrogen in California that they pay so much for is still gray. It's not blue. It can be decarbonized power generation. You can decarbonize industrial process. A lot of work going on in using hydrogen for cement and steel processing. It can be a bridge to ultimately perhaps more and more green hydrogen in the mix. So it's straightforward to demonstrate and competitively economic to achieve. I can come back to this, but there's an SB forum about hydrogen coming up in May. They're looking for people to apply as we speak. Please send me an email if you want more information about that. So let me just spend a couple minutes about the enhanced geothermal system that we favor. And there's work going on in this direction at UT as well. I've talked with Professor Sharma about this a bit. But you know the wells that have long horizontals with lots of transverse fractures. So here I'm looking at more of a Canadian configuration because they'll do this kind of thing. And so we've got a pad and we've got a bunch of these horizontal wells and then all of them with a good number of transverse fractures. So what you could do right now, where these are in hot enough formations and Haynesville and Eagle Ford are both in that category. They're hot enough for low-grade geothermal, so you can actually get electric power by what I'm about to suggest. So we suggest instead of the old idea of trying to find a network of fractures in the ground and inject cold working fluid, produce hot fluid that's been through a fracture network, create your own fracture network. And so we know from the tight oil and shale gas how to drill long horizontals, put transverse fractures. So we would say drill through the fractures. That'll give you a downhole heat exchanger, much more controlled than this, much more likely to work. And for these, let's see, did I do it? Yeah. So if you have these wells, they're going to, if they're ready to abandon anyway, how about drilling through the existing fractures to set up circulation? It looks like something like that might be cost effective. These are just many studies that my master's level student did, and she thinks your capital cost is on the order of 25 million for using existing wells that are going to be abandoned anyway, because you only need to drill the wells to intersect existing fractures, and you don't need any new hydraulic fracture. So I'll conclude this way. I'm suggesting for carbon neutral crude oil to use associated gas for CO2 direct air capture that will turn the flaring into an opportunity. The petroleum industry has technological leadership in all aspects related to blue hydrogen generation, supply, and use, and could lead the energy transition with a blue hydrogen economy. So like what they thought about back around 2003, but with petroleum industry leadership. And finally, our enhanced geothermal system with an engineered heat exchanger could use existing wells in Eagle Ford and Haynesville. And we've figured out that looks like you could, 10 of these might supply on the order of 40 megawatts power plant for about 20 years. And this is just a matter of heat transfer. So that's all those kind of calculations entail. So I think that's where we are. And I hope I left a little time for questions, even with the late start. And I hope I didn't bore you, but I just get really excited about topics that petroleum engineers could do. So can somebody help out to how we control the questions?
You bet. I can help out, Professor Ehlig-Economides. Thank you very much for your presentation. Not bored at all. Really interesting. I want to actually, first of all, let's give an opportunity for students to ask questions. Any questions from students? All right, I think I see Dr. Lake and Dr. Ravikumar are chomping at the bit. I don't hear from any students. Professor Ravikumar, would you like to ask a question?
Sure. Thanks, Michael, and thanks for that great talk, Professor. I really love it when we sort of mix engineering with some economic analysis as well. I had a quick question on your hydrogen for transportation section. Recent research and DOT surveys have shown that 85% of trips in the US are less than 15 miles, and over 90% of people who have electric vehicles charge their cars either at home or at their workplace. Given this context of how charging occurs, do you still think that fast charging, the lack of availability of fast charging is really a deal breaker, and that hydrogen will still play a big role in transportation, since most people don't seem to be charging in the mechanism you laid out?
Yep. So a couple things, personal experience. My first EVs, we still lived at a house where we could charge overnight. Perfect for urban use. Mm-hmm. But at that time, the range on those cars was small enough that it wasn't a very attractive idea to go anywhere outside of the city. Now I live in a high rise. I use public charging, which means I don't charge overnight, or I'm going to have to leave it at $1 an hour, not even still charging. It's not cost effective. So I have to worry about charging during the day.
Okay.
And so it becomes it becomes inconvenient for sure. I just think that the public are not going to like the EVs if they're going to use them as their only car. And if we're trying to come up with a solution that is to replace the current dependence on combustion fuels, then you can't say, well, I'll use my gasoline car when I cross the country, right? And that's why I think hydrogen might emerge as a very attractive solution, but we may have to go through BEVs first for people to catch on to what their limitation is. But you have, I don't know if his name is pronounced good enough, it's spelled that way, but your professor at UT is working on fast charging. If you can get to 5-minute charging, like 5-minute refueling of hydrogen, I'm going to back off. Right?
Thank you.
Uh-huh.
Dr. Lake, do you have a question?
Christine, great talk as usual. I trust you're going to make the slides available to us.
I can, yeah. Huh?
Okay, I'd like that. When you talked about the geothermal, why do you need to drill wells? Can't you just devote some of the producers to injectors?
I worry that they won't connect up well enough because it's rather random. Nobody tried to intersect those fractures from one well to another. We know they do because that's what what do you call them?
Hot frac hits.
Yeah, those are frac hits. Because my first idea was exactly that. Don't worry about drilling more wells. But I think if you really want to be sure that you get good circulation, I think you will. I think you'll get really good circulation if you go ahead and drill a well, because the fractures do overlap. So a well between two existing wells will likely intersect fractures from both sides, and there you go. You've got your circulation.
Okay, that's good, Chris. Send me your slides. Thanks. It was great. Very good talk.
Thank you.
Okay.
I'll take that from you anytime. Wow.
Dr. Delshad, do you have a question?
Yes, thank you very much for a wonderful presentation. I have a quick question. Years ago, we did quite a bit of study estimating the volume and the capacity of our subsurface for CO2. So now if we get to the large volumes of hydrogen, do you think we have enough capacity for both CO2 as CCS or CCUS and hydrogen?
So again, the beauty of blue hydrogen is that the CO2 you get from it takes less pore space than the CO2 you produce by making the blue hydrogen. So you actually have excess pore space to take over for some of the other point sources that are out there looking for pore space. Now, if you're really talking about the storage of the hydrogen, though, this is a hot topic right now. So wherever you've got salt, you can create the cavities for storing hydrogen. And the whole idea of storing hydrogen brings up the supply chain. If we migrate to more and more hydrogen use, we need to figure out a lot of supply chain problems. It's just wonderful. It's just a wonderful challenge to think about the supply chain. As I mentioned briefly, starting from existing pipeline infrastructure, and if you're going to be able to work in the renewable hydrogen as well, that storage might not be near salt cavity opportunity. And so people are looking at hydrogen storage in depleted reservoirs or various ideas with some concerns about possible microbes that might take you to H2S or who knows what. So this is a hot topic, and I wouldn't be surprised if you have some people in your department also looking at it. I know the Europeans are, we are. So yeah, storing hydrogen is going to be a very interesting challenge for sure.
Okay, thank you very much.
It's not a reason not to do it. It's just we need to get after it.
Right.
Thank you very much, everyone, for their questions. Thank you very much, Professor Ehlig-Economides, for visiting us. Our only apology is that we couldn't offer you hospitality of joining us on the 40 acres and some barbecue or something like that. So
yeah, I really would have loved to come. And so, one of these days we're going to get back to more in-person stuff and back to normal, but I still appreciate the invitation very much. And so thanks again for inviting this, and hope to see you guys on your own turf one of these days.
thank you very much.